Thank you, thank you. Well, that was a lovely introduction, wasn't it? It went on a bit too long, but I didn't mind. This evening I'm going to talk about, well, you see, I've borrowed from Donald Rumsfeld the subtitle, because I'm going to talk about essentially the contents of this book, The World According to Physics. It's not my most recent book. I think there may have been some confusion in the blurb. A book came out this year called The Joy of Science, which I was a bit concerned about because when my publisher, my editor said, "We've got a great title." It's based on this book, a cookery book in America. I forget the name of the author in the 1950s, The Joy of Cooking. And he said, "We call it The Joy of Science." I said, "You do know there's another book, The Joy of, which begins with an S." And she said, "Oh, yeah, good. Oh, that might help with sales, maybe." But anyway, I'm talking about, this is the book before last, The World According to Physics. There are many books, popular science books, on physics. Those of you who read and follow popular science will know that every year there are probably a dozen or more good books that tell the story of what we understand about the universe and about reality. Many of them are very big books, over 1,000 pages. This one is small, it's almost pocket-sized, and so if we think about our knowledge of the physical universe as an island, these books will explore the whole island. They will tell the history of how we came to understand what we know, and they try and cover all aspects. This book is a walk around the shoreline of the island, the edges, the limits of what we currently understand, and what there is out there that we still need to understand. So I'm going to try and get through. I'm not going to be able to cover all areas of physics in 45, 50 minutes, because I want to give some time for questions, but I'll see what I can do. I want to start with this article by Stephen Hawking. So this was in 1981, over 40 years ago, predicting the end of theoretical physics. So he says, in this article, I want to discuss the possibility that the goal of theoretical physics might be achieved in the not-too-distant future. He was talking by the end of the 20th century. This was just before the big revolution in what we call superstring theory. But that was the mood in theoretical physics in the last few decades of the 20th century. They felt, we're nearly there. We nearly have a theory of everything. A theory that unifies all the phenomena and the forces and behavior of the physical universe into one equation you can wear on a t-shirt. And, of course, it reminds us of what physicists thought at the end of the 19th century. Because, again, by the 1890s, well, we have electromagnetism, we have Newtonian mechanics, we have thermodynamics and statistical mechanics. We know everything. And then they discover the electron, they discover X-rays, they discover radioactivity. And then Max Planck kicks off the quantum revolution, and Einstein comes out. And they realized that actually what we thought was the explanation of everything was a long way from what we now understand. We were a long way from the end. And I would argue that, again, we are actually a long way from the end. That Stephen Hawking was wrong. We are not near the end of being able to unify all our theories. If I think back during my career in physics, what new discoveries, exciting changes, what is there the equivalent of the discovery of the X-ray and radioactivity and the electron, the end of the 19th century? Well, here are two, probably the most popular, famous examples. The confirmation, discovery of the Higgs boson at the Large Hadron Collider in 2012, and a few years later, the discovery of the first gravitational waves at these big experimental facilities, the LIGO facilities in America. Both of them quite correctly made headlines around the world. Everyone was talking about the Higgs boson. most people don't understand, even most physicists don't actually understand what the Higgs boson really is, but it's exciting. We all knew we discovered it. Discovered gravitational waves, Nobel Prizes to everybody. The problem is, of course, neither of these discoveries was a surprise. Peter Higgs and others, he wasn't the only one, even though the particle was named after him, they had predicted the existence of the Higgs field, the Higgs mechanism, and the Higgs boson back in the 1960s. Half a century they had been waiting for the experimental physicists to build a machine, the Large Hadron Collider, that could create this particle and prove that their theory was right. But it wasn't a surprise. Gravitational waves, even longer. Einstein's general theory of relativity, back over 100 years ago, almost exactly a century before the discovery, was predicted. If general relativity is correct, there should be these things, gravitational waves from big disturbances of matter in the universe, sending ripples through space. So again, it's a tick the box. Yep, found Higgs boson, found gravitational waves, great. It would have been more interesting if we had not found the Higgs boson. Not for the guys who were working at the Large Hadron Collider who had invested their careers in it. They were very relieved and excited and very happy. But for many other physicists, it would have been more interesting, actually, if the Higgs boson didn't exist, because it means there's something missing in our current theories, and we need to go back and think up something new. More Nobel Prizes. The only real surprise in the last few decades in physics was back in 1998. And that was a discovery of dark energy, this mysterious force pushing the universe apart. Discovery by astronomers that the universe is actually expanding faster now than it was in the past. We'd known, until then, until 1998, all the textbooks would say the universe began with the Big Bang and it's been expanding, but ever since then, gravity has been slowing down the expansion. Everything's pulling everything else together, stopping it from spreading out from each other. Then in 1998, they discover, by looking at the most distant galaxies in the universe that we can see, they're moving away from us at a speed that suggests that they're moving away faster. The universe is stretching faster now than it was in the past. That needed explaining, and it still needs explaining. So this is one example of something that Stephen Hawking, certainly when he wrote that article in 1981, certainly couldn't have predicted. By the way, this picture here was produced, I wrote, I don't know if you have it in Denmark, they're called ladybird books. They're tiny little books where they have one page of text and one page of illustrations. And they're meant to be for children, but adults like them as well. And it was very nice. So I wrote a ladybird book on gravity, and the artist was very talented, so he produced it. So I had a page talking about dark energy, and he produced this lovely image of something from Star Wars. So there are things we don't understand, and even now in popular science, certainly, but also in serious physics and cosmology research, there are still questions that we don't know the answer to, we can't agree on. Dark energy is one. There's also dark matter, which is a different thing. Dark matter is not the same as dark matter we've known about for a long time, but we still don't know what it is. We don't know what it's made of. But there's also things like the question of the Big Bang itself. No physicist or astronomer or cosmologist who has studied the subject enough would argue about the Big Bang. We all agree our universe started from a very hot, dense initial state. But can we ask the question, what was before the Big Bang? And I get, when I give talks to school kids, they'll say, oh, yeah, but the Big Bang, yeah, but what made the Big Bang? What happened before? You know, if you are religious, if you have religious faith, you say, well, there was some supernatural divine creator that pushed the button, created, and then that's it, explains everything. But it wasn't even a question that was allowed in science until recent years. The usual answer was this. You go back earlier and earlier and earlier in time. The Big Bang is the moment that space and time themselves were created. And so it's the same as, so you can't say what was before the Big Bang, because there was no time to put the word before in. Right? That was the beginning of time. It's like saying, walk to the South Pole, and when you reach the South Pole, keep walking south. Doesn't make it right. Every step you take from the South Pole takes you back north again. It's the furthest south you can go. It makes no sense to say what is south of the South Pole without leaving the Earth. So in a similar way, what is before the Big Bang makes no sense. Despite that, in recent years, that has also been questioned. There are ideas in cosmology suggesting maybe there was a before the Big Bang. In fact, the idea used to be that there was the Big Bang, and then the universe expanded. Space sort of expanded as time went on. And matter cooled down, and atoms, and then stars were created. But to explain some of the properties of the universe, cosmologists invented this concept called inflation, where just after the Big Bang, space expanded very, very quickly, just to smooth things out. We needed that much quicker expansion, just for a tiny fraction of a second, and then the expansion slowed down to a more normal pace. Well, of course, now there's another idea that maybe the inflation happened before the Big Bang. Maybe our universe is just a bubble in a much bigger, what we regard as the universe is just a small part of everything, the multiverse. And maybe the multiverse is constantly undergoing inflation. In fact, it's called eternal inflation. And then every now and again, there'll be a bubble appearing in this eternal inflation, and that's a Big Bang of one universe. And our universe, everything we see, is just one bubble in this multiverse of universes. So this, so this is another picture from that Ladybird book, which I quite like, me making bubble universes. Again, I just tell the artist, I say, well, multiverse, bubble universes, and he says, okay, leave it with me. I'll do something artistic. So our journey in terms of what we know now, and we know we haven't reached the end of the road, has been, certainly since the beginning of modern science, since the scientific revolution in the 16th, 17th centuries, has been a journey of unification, finding different phenomena and things in the universe to explain, and realizing they're connected with each other, realizing they're part of some deeper truth that simplifies, I guess, our picture. So this is a slide. I'm very happy it's a very big screen, because the fonts I use are quite small, and I fill it up. When I'm giving a talk on a small screen, I can't tell the words, so it's good. You can enjoy it. Okay, so this is the journey through evolution, through unification. Start off in the top corner. That's the size. See? Now you know what I mean. I'm gonna fill it. Probably the first, in modern science, the first idea of unifying concepts that were regarded as being very different was by Isaac Newton, who comes up with his law of gravitation. He says the apple falling to the ground is experiencing the same force as the force that keeps the planets in orbit around the sun and the moon in orbit around the Earth. I mean, until then, no one thought why would that be obvious? The forces of nature governing the heavens should have nothing to do with why the apple would prefer to be lower down towards the ground. So he unified those two ideas. Okay, then 19th century, middle of the 19th century, people like Michael Faraday and James Clerk Maxwell realized that electricity and magnetism, which we know what electricity is, we know what magnetism is, they're actually part of the same, they are described by the same fundamental force, the electromagnetic force. So again, we have some unifying ideas. Then we jump down here. Again, 19th century, second half of the 19th century, people, well, throughout the 19th century, people were working on the idea of heat and work and energy and the power of steam and developing engines. And then that gets unified with an idea called statistical mechanics. People like Ludwig Boltzmann working on this. And they are unified when today, what we teach to physicists at university is a subject called thermodynamics. Okay, and it's essentially the idea of heat and temperature and pressure and how you describe matter at the larger scale in terms of fundamental particles interacting with each other. Okay, we jump up to here. No surprises. Who made the connection between space and time? That was Einstein in his special theory of relativity in 1905. Of course, in that same theory, he shows that matter and energy are equivalent, interchangeable. But we've now hit the 20th century. 10 years after Einstein's special theory of relativity, he applies it to gravity and replaces Newton's picture of gravity. He says, Newton thought gravity was just this invisible force that pulls objects together. Einstein says, no, it's not a force at all. Gravity is the shape of space-time. It's geometry. And general relativity, to be fair, is not an easy subject. It's only taught to students in their last year of university, typically. Einstein had to go and learn the mathematics before he could develop general relativity. So that was tough. But it was one of the great triumphs of 20th century physics. Okay, we now jump down to, so general relativity gives us cosmology. And I want to jump down here, you can see it on the left. Atoms. The existence of atoms wasn't really confirmed until the beginning of the 20th century. In fact, also due a lot to the work of Einstein. By the First World War, people like Ernest Rutherford were now being able to see inside atoms. They could understand the structure of atoms, and it was made of a nucleus with electrons going around it. And then by the 1920s, the early work on quantum theory became quantum mechanics. And since you are from Copenhagen, you will know that your city played a big role in the development of quantum mechanics, because Niels Bohr, having worked in the UK, in Cambridge and Manchester, he comes back to Copenhagen, he gets money from the Carlsberg Brewery to build his new institute in 1920, and he brings together the great geniuses of the time. Werner Heisenberg, Wolfgang Pauli, Erwin Schrödinger, Enrico Fermi, these great names that every physicist admires, that they are our heroes. They developed quantum mechanics, the theory that describes the subatomic world, the world of the very small. General relativity describes the very big, quantum mechanics the very small. Two very different theories. By the late 1920s, quantum mechanics and special relativity are joined together. And we have something called quantum field theory. Right, now I'm going to speed up because I've got to fill up the rest of the screen, and I don't want to use up all my time. So, electromagnetism combined with quantum field theory gives us something called quantum electrodynamics. By the middle of the 20th century, people like Richard Feynman have developed this theory. So you can see lots of words on the left, fewer words as I move across to the right. Nuclear physics. We find inside the nucleus two new forces. Until then, there was gravity and electromagnetism, just two forces. Now we discover two new forces. They have to be explained. They're explained using quantum field theory. So we have something called quantum chromodynamics. Quantum chromodynamics and quantum electrodynamics, quantum chromodynamics and the weak force gives us electroweak theory. Finally, we combine all the quantum stuff together, and we have what's called the standard model of particle physics. And at the very top, cosmology, we have the standard model of cosmology. Don't worry about the lambda CDM. It's just that's the best we can do to describe the universe at large. The standard model of particle physics, best we can do to describe the very small. Of course, standard model of cosmology still has things to be explained. Dark matter and dark energy. We still have to understand them. But, and this is what Stephen Hawking was hoping for in his comment about the physics coming to an end. He was hoping to combine the cosmology and the particle physics together into one theory of quantum gravity. So quantum gravity is the small connected with the large. Sometimes it's called a theory of everything. We don't have it yet, which is why I've put a dashed line around it. We're still looking. One argument, which I'm actually quite in favor of, is that we're not going to get a theory of everything unless we bring in that third pillar, thermodynamics, as well. But maybe there are other areas of physics that are going to have to be involved as well. So I just wanted to fill up some white spaces. So there's quantum information theory, there's nonlinear dynamics, non-equilibrium thermodynamics, there's the black hole information paradox, which is a whole other lecture, which I'm not going to go into. So lots of dashed lines, lots of question marks. We are nowhere near Stephen Hawking's dream of the end of theoretical physics. In fact, to show you one other picture from the Ladybird book, this is depicts the struggle between the two leading, potentially, or have been for some years, leading contenders for a possible theory of quantum gravity, depicted as superheroes having an arm wrestle. So on the left, there's the string theory that wants to unify the forces of physics. On the right, there's something called loop quantum gravity that wants to see how space-time itself comes about, how it's created. There are lots more people working on string theory than loop quantum gravity. In fact, there have been several books out in recent years criticizing string theory, partly because it hasn't led to the success that people had hoped, but also in part out of jealousy, because string theory has sucked all the cleverest physicists to work in that field, and all the other physicists working in other areas, why is string theory getting all the bright guys? So, but they haven't had the success that it was hoped they would have 20 or so years ago. So are we at the stage now where we have to maybe take a step back and try and understand or re-examine the most basic ideas about reality? What is space itself? It's a long argument about whether space is a real thing. So people like Aristotle and Descartes argued that space isn't real. It's only defined by being the distance between things or being the volume inside something. Isaac Newton said, no, space is a thing. Space is real. It's the fabric. It's the canvas. It's the stage on which the universe is built. Imagine you have an empty box, complete vacuum inside it. I mean, I know in quantum language, I should say there's always something. There's always particles popping in and out of existence. But let's just imagine it's completely just empty space. Does the box exist if I remove the walls? Was that space only real because there were walls to define it? What about if I put the box inside a larger volume, also empty, and now remove the walls of the inner box? Is its space now real because it's forming part of the larger volume inside the larger box? These are questions that sound trivial, that sound almost childish. Surely we have figured out what space is. Well, the best answer we have so far is what Einstein tells us. Now, Einstein published a book called Relativity, the Special and General Theory. He published it first in German. In fact, very soon after he published his work on general relativity. And it's almost like a popular science book. It's not a textbook as such. It was translated into English and other languages. And there were many editions of this book. But usually when a book comes out in new editions, the author changes some things and updates them. With this book, Einstein didn't change anything from the original. He just added appendices at the end. And appendix number 5, the most famous one, appeared the year before he died. That was the last addition to the book. And in it, he gives a definition of what space is. He says, if we imagine the gravitational field to remove, if we take gravity away, so we take matter and energy away from the universe, so there's no stuff, therefore there's no gravity, there does not remain any space-time, but absolutely nothing. So he's saying that Aristotle and Descartes were right? That without matter, without the walls of the box, there is no space-time. He also says space-time does not claim existence on its own, but only as a structural quality of the gravitational field. So you need stuff for space. In Einstein's language, we have to talk about space-time to actually exist. And yet, he also points out that Newton is right, because space-time is a real thing. It could be stretched and bent and twisted and warped through the action of gravity. But for Einstein, space-time is the gravitational field. His equations of general relativity, it's an equation, so it has an equal sign with something on one side and something on the other. On one side is matter and energy, mass and energy, and the other side it's space and time. And you know from school, primary school maths, with an equal sign, if one side is 0, the other side is 0 as well. Okay? They're equal. So if you take away matter and energy, there's no space-time. Take away space-time, there's no matter and energy. Is that the end of the story? Well, no, because one of the things that I've been talking here about general relativity, I've been missing the other big theory of 20th century physics, which is quantum mechanics. And the whole point is how to bring quantum mechanics and general relativity together. And then the story really changes. In fact, I've asked, what is space? I might as well ask, what is time? And there are lots of jokes about, what is time? And it's just nature's way of stopping everything from happening at once, is one definition. But the different areas of physics all give, the different pillars of 20th century physics, all give different definitions of what time is. So general relativity says time is part of the fabric of the universe. It's part of space-time. It's a dimension. It can be stretched and warped. Okay, it's an axis in 4 dimensions. Quantum mechanics says time is a parameter. It's just a number. You plug into your equation. You can run your equation forwards. You can run it backwards. It's no more profound than that. And then you have thermodynamics, which says, no, time isn't a dimension or a number. It's an arrow. It points in a certain direction. It points from past to future. Until we can reconcile these 3 ways of thinking about time together, I don't think we're going to be able to unify physics. In fact, the search for a theory of everything we talk about, unifying general relativity and quantum mechanics, well, even Einstein himself argued that actually thermodynamics might be the most important idea. He says, thermodynamics is the only physical theory of universal content, which I'm convinced would never be overthrown. So even Einstein's admitting we may have to change general relativity, we may have to tweak or modify quantum mechanics to get them together. But thermodynamics, that's sacred in as much as a physicist can talk about something as not open to discussion or debate. So I want to focus a little bit about this idea of time and this arrow of time. And I want to talk about it a bit because, and I will say at the end of my talk, how am I doing for talking about time? Good. Okay, about 15 or 20 minutes. It's the current area of my own research, trying to understand the nature of the direction of time. Why is there a past and a future? And this goes back to an idea called Loschmidt's paradox. We're aware that time has a direction, and you might even think that's a trivial, a stupid question. Of course time goes from the past to the future, because the past happens before the future. You can't go backwards. And yet, all the fundamental equations, the dynamical theories of physics, don't care which direction time goes, forwards or backwards. They work. They say the laws of physics are the same in either direction. Only the second law of thermodynamics is what gives us the arrow of time that says time has a specific direction. So if you think about the orbits of the planets around the sun, we know they go around the sun sort of anti-clockwise in this picture from looking down from above. Well, actually, even from below as well. But if they went round the other way, it wouldn't break any laws of physics. It could have been possible for them to have gone round the other way. Particles moving around in a box, that random motion of particles bumping into each other. If I told you I'm starting to run this film backwards, it won't make any difference to you. So describing these phenomena using equations of statistical mechanics or Newtonian mechanics doesn't matter. There's no direction to time. Particle collisions, this is called a Feynman diagram, for those of you who are not familiar with it, but the arrows show the direction of particles, A and B, coming together. They feel some force, the dashed line, and then they move apart. Maybe that force changes those particles into new particles, C and D. But the laws of physics down at the particle level says, well, in that case, C and D could also come together, interact, and create A and B in the other direction. That's also possible. But in our everyday world, we have an arrow of time. We have ice that melts. Water doesn't freeze unless you do something to it. If you put a glass somewhere and isolate it, the ice will eventually melt in the water. It doesn't go the other way. Air leaks out of a punctured tire. It doesn't come back in again if the pressure is different. An atom or an atomic nucleus undergoes radioactive decay. It spits out alpha particles. You don't see alpha particles coming from outside, ending up inside a nucleus. Heat radiates from a hot object. Objects slow down due to friction. Chemical reactions very often move only in one direction and not in the other. These things can all happen in reverse, but it's very, very unlikely. And they're all described by the laws of thermodynamics. So this paradox says, well, where does this arrow of time come from? What's its origin? The usual answer, which cosmologists will tell you, and they have a valid point. I mean, there's certainly, I don't know if anyone listens to the podcast Mindscape by Sean Carroll, American physicist, very eloquently explains this standard answer. He says, well, time flows in the direction of increasing entropy. So entropy is the amount of disorder or the amount of information gathered about a system. But let's keep it to a simple definition. If I have a pack of cards that is all organized in suits and numbers, 2, 3, 4, 5, all the way up to an ace in each suit separately, and I shuffle the cards, I'll mix them up, right? That is in direction of increasing entropy, the increase of disorder of the cards. Now, it is possible By further shuffling, I would get back to the ordered state again, but it's very, very unlikely, and you can calculate the probability of it. It'll take longer than the age of the universe, and I'm just not that patient. But that's the direction of increasing entropy. The direction of time is the direction in which cards become more shuffled, more mixed up. It's the direction in which your cream mixes with your coffee, not the opposite. So you can't run those films backwards. You would see there's something wrong. Right? But then why? Why does entropy increase? Well, the standard answer is, well, because it was lower in the past. Okay, well, is that an explanation? Well, why was it lower in the past? Because it was lower before that. Why was it because it was low? And you go all the way back, and you say, why does the egg get broken, become an omelette, and you don't get the other way around? Because entropy was very low at the Big Bang. So that's called the past hypothesis. Some people might find it satisfying, some people might find it mind-blowing, some people might find it ridiculous. The reason you can make an omelette but you can't remake an unbroken raw egg from an omelette is because entropy was low at the Big Bang 13.8 billion years ago seems a bit strange. And I don't think it solves the problem. So the problem is that all our equations of physics are symmetric in time, right? So you're given a moment in time, you run into the future and you see how things change. If you run into the past, they will change in the same symmetric way as they do in the future. You can run it forwards and backwards and nothing changes. Well, all we're doing is saying that special moment, so entropy increases into the future, but these equations would say, well, entropy will also increase into the past because you have to have symmetry. So how do we get rid of this crazy idea that entropy increases in the past, move that special now moment, put it right at the beginning, and then only worry about things happening in its future? You don't have to worry about the past because there was nothing before the Big Bang. It seems cheating. Which is why I'll come at the end to say something about what my current thinking is on this subject. Okay, I want to say something about, well, this is my pick. This is quantum mechanics, right? So a wave function, cats in boxes. That's all I need to show, quantum mechanics. Quantum entanglement, as I think you heard in the little intro video, and so I won't repeat again about Einstein and spookiness, because that gets used too often. But the idea is, it used to be a rather strange idea in quantum mechanics, and it wasn't really taught to students because we didn't think it was important enough. That two quantum particles, like two electrons, could somehow, their fates are intertwined, they're interconnected, that's such that you can't describe them separately, you have to describe them both together. And this means if you influence one, if you look at one or change it or measure it, you're immediately affecting the other one. We're now beginning to understand that quantum entanglement is actually a profoundly important idea that may play a role in finding a theory of everything, may play a role in understanding the arrow of time. So I want to quickly run through this really nice idea, which I hope is right, but it's not my idea, right? So, but it would be cool if it's correct, but that's not good enough in physics, unfortunately. Anyway, most famous equation in physics, boring. Here's this nice equation. Some of you may have heard of it. If you're a physicist, you may well have heard of it if you follow popular science. Usually you see something like this and you think, okay, I know algebra. E cancels with E, R cancels with R, I know, so 1 equals P. Well, that's even more boring than E equals MC squared. That's not what this is. You see, this is not an equation. These letters don't symbolize physical quantities like energy or pressure. They are the initials of physicists who came up with two very clever ideas. This is a paper that was published in the 1930s by Einstein, Podolsky, and Rosen, so E, P, and R. And they were asking a question about this idea about quantum entanglement. Let's see if did I have, no, I didn't get past that, okay. So they were questioning whether quantum mechanics was complete. They didn't really believe this idea of quantum entanglement. And so they published this paper in 1935, it gave rise to what we now call the EPR paradox. And I will go through it it'd be really good to go through the EPR paradox in 2 minutes. But let's see. All right, imagine you have a box that can produce two particles, say photons, particles of light, back to back. Okay, they fly out and they reach some distance apart. I've drawn them like this because they're not particles and they're not waves, they're some sort of in-between thing, depending on how you look at them. Imagine we want to examine photon 1. We take our instrument, our detector, that measures the wavelength of the light. Now that means it's measuring the energy or the speed of the light. It tells you where it is. It tells you what its frequency is. Now that means it's seeing that photon as a wave. Since the photons came out, they're created from the same source back to back, they're both traveling, they both have the same energy. So if we know the wavelength of the light, photon 1, then that means we also know the wavelength of photon 2. So without looking at photon 2, we can say it has this wavelength. But we could have chosen to measure the position of photon 1. That means we're doing a different experiment. We now have a detector that doesn't look at the wavelength of photon 1, but where it is. It sort of captures it and finds out exactly what its position is. So now it's measuring the photon as a particle. Well, if the photons are both traveling as particles back to back with the same speed, then photon number 2 will be the same distance on the other side of the box from photon number 1. So without looking at photon number 2, we can tell you where it is. Einstein, Podolsky, and Rosen said, well, that's weird, isn't it? Sure, photon number 1's properties depend on what you measure. And this is one of the ideas in quantum mechanics. If you look at wave nature, you find a wave. If you set up an experiment to find particle nature, you see a particle. But you can't have something that's both a point particle located somewhere, but at the same time a spread out wave. And yet that's what they seem to be saying about photon 2. Without touching it, I could assign to it an exact wavelength, and I could assign to it an exact position. Therefore, quantum mechanics, which says this is impossible, Heisenberg's uncertainty principle and all that business, can't be right. That was their argument. But of course, since then, we've realized that photon 2 knows what you're going to do to photon 1 and behaves accordingly, because photon 1 and photon 2 are quantum entangled. Physicists tend to be able to get around this with clever language, because the usual question is, how can photon 2 immediately, instantaneously know what you're doing to photon 1? Surely this means some instantaneous, faster-than-light connections. This is what Einstein didn't like. And physicists say, well, you can't use it to send signals faster than light. It's only at the quantum level, at the mathematical level, that they are instantaneously connected. Don't worry about it. But if they're honest, they are. These two photons could be on either side of the universe. And I measure one, and that influences the spin of the other. I can't predict in advance what it's going to be, because they're subject to quantum probabilities. But in recent years, there's been an idea that suggests maybe this can be explained, because there was, within a few weeks of Einstein, Podolsky, and Rosen publishing their paper, two of them, Einstein and Rosen, published another paper in which they were trying to understand some problem with general relativity. So not a problem with quantum mechanics, but a problem with the very large. And the problem there was general relativity predicts the existence of black holes. And black holes, so the theory in its simplest form suggests, at their center is what's called the singularity, a point of zero size, an infinite space-time curvature. And Einstein said it doesn't like zero size, it's because that means it has infinite density. It's like dividing by zero on your calculator, or for young people on your smartphone. So Einstein and Rosen changed it. So what if the middle of a black hole isn't a point? What if it's a tunnel, a bridge, which became known as the Einstein-Rosen bridge? Those of you who've seen Avengers Endgame, which I rewatched the other day, by the way, which is why I remember, they talk about Ant-Man says, "Oh, yes, so you mean an Einstein-Rosen bridge?" They clearly had spoken to physicists to get the dialogue sounding sciencey. So within a few weeks of each other, Einstein and colleagues, they publish a paper on the EPR paradox, and they publish another paper on the ER, Einstein-Rosen bridge in general relativity. The idea there is that you have, imagine 2 points distance in space, A and B. They're very far, but if space can be bent over, then the distance between them is much smaller. That's what we now call a wormhole, right? Okay, so the Einstein-Rosen bridge was the old idea. Then when people like Kip Thorne, cosmologist in America, worked on it, it became, in popular culture, known as the wormhole. So, here we go. So in 2013, two American physicists, Juan Maldacena and Lenny Susskind, published a paper. You can't tell from the title, Cool Horizons for Entangled Black Holes, exactly what their trick is. But it's a really neat idea because they bring together those two ideas. Imagine you have two ends of a wormhole. So these are not two black holes. If there are black holes, those circles will be black, right? Because no light can come out. But these are meant to be what are called traversable or Lorentzian wormholes. So what you're seeing through this mouth of the wormhole is what the universe looks like out of the other end, and vice versa. Where is the tunnel between them? Well, it's outside of our space, right? So we can't see it. But we can see it if we collapse our space into 2 dimensions. So if I flatten space out, I add some grids just so that it looks physically, all right? And then we have the wormhole between them. Susskind and Maldacena's idea was that what if the two entangled photons in the EPR paradox, or any two entangled particles, are in fact only able to communicate seemingly instantaneously with each other if they're joined by a quantum wormhole. So the idea is that the reason why entanglement seems so strange is because what we can't see is that those particles are interconnected by this network of wormholes. That's the origin of entanglement. It's a beautiful idea in its simplest form because it says that entanglement is the thread that produces the fabric of space-time. It's quantum entanglement is that holds and creates space and time together. But those are just words, and particularly very simplistic words, because the theory hasn't been worked out and evolved completely yet. But it may be the whole of space-time is really just some quantum foam, lots of wormholes popping in and out of existence, connecting things together. I wanted to end very quickly because I've already gone beyond my time and I wanted to give you a chance for questions, but I was asked by the organizers to say a little bit about my own current research. So I'm based at the University of Surrey in Guildford, just south of London, and we've set up a quantum foundation. So we've got a big
research grant from an American foundation called John Templeton Foundation. And we had this really cool title of our project. We basically said, right, we're going to give you some really, really sexy words, give us lots of money. And so we said, life on the edge, quantum thermodynamics, quantum biology, and the arrow of time. So, but it's a big collaboration. 6 universities are involved in it. And I'm finding where, over the last 20 years, I've done a lot of work in broadcasting, as you saw in the intro, a lot of stuff for the BBC, TV, and radio. I'm now shifting back to doing more research, and I'm, apart from coming and giving talks to lovely audiences like you, I'm getting back involved in a lot of this research. So for me, there are two of the big problems we're thinking about. One is this idea of the arrow of time. Where does it come from? I don't want the arrow of time to be defined by entropy being low at the Big Bang. I want to see if it can emerge dynamically out of our equations of quantum mechanics. Again, listen, this is not my fault. The organizer said there will be people in the audience who would appreciate a little bit more technical stuff. So for most of you who are not physicists, I apologize. I'm doing it to satisfy the geeks out there who might appreciate it, right? So when we teach quantum mechanics, we typically teach it as an isolated quantum system. It's always one-dimensional. It's always square barriers and square wells and stationary states. Boring. No system is isolated, and what we really should be solving is what's called this lovely thing, the master equation. So there's lots of ways of writing this. I've chosen to write it in this form. The first term, what's called the von Neumann term, if you rub out everything else to the right, that's just another way of writing this Schrödinger equation. But this new equation tells us that no quantum system behaves by itself. Everything is entangled with everything else. Everything is connected with everything else. So it allows us to study things like entanglement. It allows us to explore the idea of possibly an arrow of time emerging. Quantum system entangled with its environment, the environment itself, just the surrounding air surrounding an atom is measuring it. And by measuring it, it gathers information about the system. And so there's lots of words there in red. It's an area, so I started my research field as in nuclear physics, and I've gradually moved off into a slightly new field. I'm starting, finally, when you've started to make some progress in a new area of research, when at least you can start to produce papers. So, so the first authors were my PhD students. They do the hard work. I just pat them on the head and say, you're doing a very good job. That's what professors do. But then the other area is this new area of research, which could have been a whole other lecture I could have told you, but I chose to talk about this one. Quantum biology, the idea of finding quantum effects in living systems. So Erwin Schrödinger, back in the mid-40s, wrote this book, What is Life? And he suggests that living systems behave thermodynamically or have a behavior just like inanimate matter near absolute zero. And we know when inanimate matter is cooled down to near 0 Kelvin, it starts to exhibit quantum effects, when you can calm down all the thermodynamics. Well, Schrödinger said in living systems, inside a living cell, there's ordered structure. It's low entropy. It's behaving like inanimate matter near absolute zero. Therefore, maybe quantum effects might be involved. It was just an idea, although that was a famous book. Well, a few years ago, 2015, I co-wrote a book called Life on the Edge, which is where we stole the idea for our project title from, with a molecular geneticist, John Joe McFadden, who's a colleague of mine, where we talk about now suddenly there's this new emerging interdisciplinary area of research where we're looking for quantum effects inside living systems. And the area that I'm most interested in with my collaborators is the idea that you can see proton tunneling between strands of DNA. So DNA, the double helix, is held together by hydrogen bonds, basically protons. And those protons can jump from one strand to the other. And if they do, that could lead to a mutation. And so it's important to understand genetic mutations if they're caused by proton tunneling. And it's a nice area of research because we're doing theoretical physics, lots of quantum mechanics, we're doing computational chemistry, and we're applying it in biology. So that's the other area of research that I'm involved in. Good, I have run over time. I'm very happy to answer questions. I'll leave you with this. I'm putting this up not for publicizing for me, obviously. My publishers asked me to put this up, so I'm only doing as I'm told, because it would be rude not to. But I will end there. Thank you very much for your attention. I'm happy to take questions if the organizers believe there's enough time, and happy to answer questions afterwards if you catch me drinking a Black Holes cocktail after this talk. Thank you all very much.